Okay, welcome to another session of the reading group for the assumptions of physics. We are waiting to see if a couple more people join. There you go, Alina is joining. Let's give it a few minutes too long. And I should start doing all the things that I need to do anyway. Share the link on the chat and then share the text. There it is. Okay, there we are. So while we wait, maybe I can give another recap to see where we are. So last time, if I remember correctly, we started the relativistic mechanic. Hi, Mr. Slack Muffin. Yes, it is Pinimola. So okay, so we had first thing that we did was we extended phase space not just by t but also by e, and we saw that to be consistent with all the stuff that we saw before on the Lagrangian, the e actually had to have a minus sign, and then we basically did standard what it looks like standard Hamiltonian mechanics in the Q alpha and P alpha. So we're just extending the phase space with the temporal degree of freedom. And what we found is that the sort of the analog of the Hamiltonian now is called the Hamiltonian constraint, because it's not just something that sets an initial condition that then is conserved. It's really something that it's has to be equal for all states, and basically typically one would just set the Hamiltonian constraint so that it goes to zero. And we saw that for a free particle, it's basically the norm of the for momentum plus m square and c square. So essentially the Hamiltonian constraint is essentially fixing the norm of the for momentum. And then we saw that through the equations, you recover the fact that for at least a free particle, conjugate momentum is equal to kinetic momentum, where kinetic momentum now is defined by the force velocity, and the force velocity is calculated with an affine parameter s. So we saw that the Hamiltonian constraint generates motion through an affine parameter. So one can reformulate the Hamiltonian constraint to be different, and you get a different parameter, even if the numbers are exactly the same. And then we basically went back and tried to understand the link between the Hamiltonian constraint and Hamiltonian themselves. And we saw essentially that you can always go from one picture to the other, and that the Hamiltonian constraint can be understood as essentially a multiplication of different Hamiltonian that live on disconnected part of phase space. And think that was it. And then we saw that we can define a symplectic form on that space, and that everything sort of works as one would expect, with the difference is that this minus sign is basically physically means that the temporal degree of freedom does not give us new configuration. And so whenever we are counting states in the extended phase space, we have a correction because, again, we don't want to double count states because the temporal degree of freedom does not really create new states. So, question from Luis. How are you defining space? Is this assuming an inherently 3D universe? So this is phase space. So it's basically the pairs of let's say position of momentum. It's pair of conjugate quantities. In this setting, there is no assumption of how many particles are there, how many how many spatial degrees of freedom are there for each particles. We don't know that. Like we just have a bunch of variables that are conjugate to each other, and they evolve according to Hamiltonian evolution, which we saw it was equivalent to assuming deterministic reversibility. So at this point, we're not assuming that there is even a 3D universe. Okay, so that was I think what we had last time, and this today we are basically going to relook at the kinematics in the context of the extended phase space. So we are going to see essentially what we did when we did the full kinematic equivalence. We showed that we were able to recover massive particle under scalar and vector potential forces. We are basically going to do the same thing just in the relativistic setting, so that we basically find the sort of EM field like forces. Okay, shall we start? Artem?
So it is time to add assumption of kinematic equivalence. In this generalized setting, the trajectory and therefore the velocity will be in terms of the affine parameter s. Therefore, we set the derivative of q alpha with respect to s equals the derivative of q alpha with respect to time multiplied by derivative of time with respect to the affine parameter. And then we just write down the components of that derivative with respect to time. And we see that, yeah, so the spatial components are just the velocity, and the first component we leave it the same.
Yeah, so in principle, since Q0, we typically assume that it's T itself. That first component is just going to be 1. So you're effectively, if you studied a little bit of projective geometry, like there is this way that you have points at infinity and then you rescale them, or that's essentially similar to what's happening. Like the one, that one there is the renormalization of the vector.
Given that the Hamiltonian constraint on the extended phase space plays the same role as the Hamiltonian on the standard phase space, we will have an equivalent principle of stationary reaction once kinematic equivalence is taken. The action can be written as A of gamma is the integral of, would that be still the Lagrangian or?
Yeah, it turns out.
Yeah.
Yeah.
The Lagrangian over this
Times the affine parameter.
path, yeah.
Yeah.
Times the affine parameter over this path gamma,
Mhm.
and then we extend this Lagrangian. So we have momentum, basically the same thing, yeah.
Yeah,
Just a
it's the same
Legendre
thing.
transform. Okay.
It is a Legendre transform. It's just that the velocity is substituted with the for velocity, and the time is not time anymore, but it's the affine parameter. And then, of course,
Under
you can re-express, as we did before, right? Because you have a derivative for like the function between time and affine parameter is invertible, then you could re-express this as time as well.
So under the full kinematic assumption, we have
Okay, so this maybe I'll talk. So if you remember, the full kinematic assumption meant that the relationship between the conjugate momentum and the velocity is linear. And then we define G alpha beta to essentially be that linear relationship with a constant m that it's there to fix the units. So this is the same exact, if you guys recall, it's the same exact assumption that we have put in however many weeks ago. And now you can solve this equation. And the way that you solve this equation is that since this is not a function of velocity, this g alpha beta, this just becomes that constant times the velocity plus an arbitrary function, which a set of arbitrary function, which are this alphas. And again, the q is just there to fix the unit. Then again, what you can do is make this expression explicit. So you put the u alpha on the other side, and you know that the u alpha are by definition the derivative of the q alpha with respect to the affine parameter. Then you use Hamilton's equation, and you know that u alpha has to be equal to the derivative of the Hamiltonian constraint with respect to p alpha. But given this expression, you also know that u alpha has to be equal 1/2 the inverse of g times p beta minus qa beta. So now you have this expression, you know you have the derivative of the Hamiltonian with respect to momentum as a function of position and momentum, and you just integrate. So here you have a function of p, and so this basically becomes quadratic since it's linear. And again, you have an arbitrary function u, that in general, this would be an arbitrary function of, again, position. I think there is a question. Is the action defining assumption the Rn derivative exists between gamma and s? Is that smuggling the assumption in the infinite precision? So is the action definition assuming the Rn derivative exists between gamma and s? I can't understand. I understand the words, but I don't understand the question. So maybe you can try rephrasing it and see if I can understand. And Artem, why don't you finish the paragraph?
Okay. If we set u equals 1/2 mc squared, this is the Hamiltonian constraint for a massive particle under potential forces. And also we have a footnote number 35. An open problem is understanding whether u is constrained to be a constant or not. Okay.
Right. So the issue here is that the affine parameter is arbitrary, and therefore there is some arbitrarity in the universe in the Hamiltonian constraint. And so I do not know whether essentially you can always choose a parametrization where where this function is essentially a constant. I do not know.
As we saw, the best way to understand the geometry of phase space is to use the state variables q alpha and p alpha. However, understanding the physics is tricky as conjugate momentum is a gauge-dependent quantity. One thing we can do is actually work on phase space with kinematic quantities and express elements like theta A with omega AB, the form, in those variables. We have q alpha equals x alpha, p alpha equals m times g times u beta plus q a alpha. So this is just the conjugate momentum, right? Written in terms of the no, I'm wrong. This is kinematic momentum, right? And then x alpha equals q alpha beta. This is the expression we got above, and then this is the Hamiltonian constraint we have above. Note how the Hamiltonian constraint in kinematic variables is always the same, regardless of the forces acting on the particle. To calculate the expression of theta alpha and the form omega AB in kinematic variables, first see how the covector basis transforms. We have, and I might need some help here.
Yeah, I'll look at that. First, I'll try again to respond to Luis. So the Radon-Nikodym derivative from measure theory must exist if something to be Lebesgue integral. The motivation is there to, okay, so we kind of discussed these things in the other section, so I'm trying to recall all of this. So we start. Okay, so what happens is we have so the whole notion of differentiability comes out as we discussed way past that we are describing what happens to probability distributions, and so probability distributions have to exist. So we are gonna have essentially not even just one Lebesgue measure, but let's assume that we just have a single degree of freedom to simplify things. We are going to have a Lebesgue measure on that space because that's the volume form from the symplectic form. And we have a notion, we have a measure that basically tells us how many states we have. And then if we have a probability distribution on that space, or even just a density distributions, like we have a bunch of states distributed, both those distributions have to be absolutely continuous with respect to the state count, because if the volume measure tells us how many states are there in a region, it would make no sense to say that I have finitely many states, finitely many probability inside the region if there are no states. So that makes all the probability measure or the statistical distribution that we put there absolutely continuous. And then the whole purpose of the dynamics is to move those distribution while preserving the fact that they are absolutely continuous. So putting all this together, it will mean that all the motions are differentiable, and the Hamiltonian will have to be twice differentiable. And so all these, the fact that we're taking all these derivatives, we are guaranteed that this is differentiable, and the p's and the alpha are also, the measure that these things give you are absolutely continuous with respect to the Liouville measure, which is the volume form that you get for symplectic structure. So there are all these things that sort of allows you to say, okay, we basically can do all these things because at the end of the day, we're not transporting points, but we're transporting essentially distribution of phase space, and so we are mapping densities to densities, and the fact that density have to be mapped, then the transformation has to be differentiable. Isn't that then assuming infinite information capacity, since you must be able to infinitely resolve space? No, the information is defined by the areas. So a finite compact area in phase space carries finite information. It's the point that would have a minus infinite entropy, and that is why these points are never things that we actually should think as like physical object. The physical object is like a very small distribution centered around the point. So it is the purpose of the count of state to also define how much information you have and to be able to correlate these two things. Anyway, we should continue with this because there is a lot of math here that we have to go through today, and we're never going to get to it. Okay, so we want to express the theta and the omega in terms of kinematic variables, so in terms of position and velocity, such that we are always talking about quantities that are actually measurable and are connected to the physics. So the conjugate momentum is not something that you go and measure. We never measure conjugate momentum. We always measure kinetic momentum. And you can see it here because we definitely measure the velocity, and then you have an A here, and this is a vector potential, so there is a gauge there. And therefore, P also has a gauge, and basically these two things put together, they cancel each other's gauge such that you get something that is actually fully defined physically, that there is no math arbitrariness that that you don't know what it is. So the way that we have to do it is we need to change these components, and so we look at what happens to the basis vectors on which these components are defined on. So these are the vector for the Q alpha. And what we do is just make the coordinate transformation. So this is just the Jacobian. And we basically have this is the Q alpha, right? And then we're seeing how the Q alpha changes with respect to the X betas and the U alpha, U gamma. So you should think of Q as a function of X and U. And now we are expressing the basis vector of EQ in terms of the basis vector of EX and EU. And the way that you do it is just using the chain rule. So this is just the chain rule. Then what happens is that when you change, we're having the transformation from the QP to the XU, the Q is not going to depend on mu because Q alpha is going to be equal to X alpha. So this part is 0. And since the Q alpha is equal to X alpha, this is just giving you a Kronecker delta. And so the basis vector in Q are the same as the basis vector in X, which is what you would expect because Q and X are still position. We're just changing the momentum to velocity and nothing else. Okay, so this is now the basis for momentum, and so we're going to do the same thing. We apply the chain rule. And now this is a lot more complicated. So this we're going to have to look at how the momentum is expressed in terms of the velocity, and we get it from here, right? This is expressed in terms of this is a position, and this is in terms of the velocity. So if we take it, we take this as a derivative with position. So this part, the G alpha beta, depends on position, so it gets a derivative, but the U and the M do not. So this is the only component that you have, the only term that you have from this. And then the Q does not depend on position, is a constant, but the A depends on position, and so you get a derivative of A with respect to the position. So this is what you get for this side. And from the other side, we need to take the derivative of P with respect of the velocity, and this is the only term that you have. And so you have the mg alpha gamma. And now there is this mess where we are basically taking these elements, right? This component, and we are re-expressing it in terms of the position and velocity. So here, if you remember, the way that the theta works is for the position you have the p's, and for the momentum you have zeros. I guess I should have repeated it here, but let's see if we go back up, we probably see it, hopefully. And if not, it's something that I should go, and there you go. So the theta A, you see, has component P alpha for the Qs and 0 for the Ps. So where was I? Here. So you just have P alpha E Q alpha, and then you just take the P alpha, and that's it. So now this is the expression of the theta in terms of the X and V, right? In the new coordinate. Now what we need to do is essentially calculating the exterior derivative and changing the coordinates of the omega. So I don't know if it makes sense to go through the whole derivation. I would vote not. If you guys want me to go through it, it's just simple manipulation. There isn't any how can I say, any insight to be gained. The thing that is interesting is that you see here that you get this partial x beta a alpha minus partial x alpha a beta. And if you have done, again, relativity, this is how you go from the what's it called, the vector potential to the from the four potential to the EM stress EM tensor. And so we can define F alpha beta as this partial alpha A beta minus partial X beta A alpha. So this is the electromagnetic field that comes out just by calculating things. And then the other thing that comes here is that we are doing this exterior derivative only on the first part on the first component of G. And so when we re-express all this mess in metric form, we have that theta A is this and 0, and the omega AB, it's in the diagonal. You can just see that this is just the metric tensor times m, while in the space-time components, you get minus q the m field minus this g alpha beta gamma that we defined contracted with the four velocity. And I have no idea what this thing is, as it will be discussed afterwards.
Did you make a video about this specific tensor, asking what it represents?
Yeah, it's one of the open problem on the website.
Yeah,
I don't know. I think, to me, it should be kind of like the inertial force, because if this is the EM force, I would expect this to be the inertial force, but of course, I have no idea.
Okay. Should I continue after that part?
Sure.
We recognize F alpha beta as the electromagnetic field tensor. However, it is still an open problem what G alpha beta gamma represents. It has a direct relationship with the Christoffel symbols gamma, alpha, beta, gamma. It's kind of like an antisymmetric version in the first two indices, I guess.
Exactly. So the thing that is cool about this is that you have the G's, right? And you are making a sort of an exterior derivative on the first element. And then you do the math, it's exactly like taking the Christoffel symbol of the second kind, I don't remember, and antisymmetrize the first two indices.
Mm-hmm. Okay.
And then, as I say in the footnote, this is not the torsion. A lot of people see this, oh, that's the torsion. No, because the torsion antisymmetrized the second two elements.
Okay. If we express the two tensors in covariant components, we find that
yeah, again, this is all calculation. The point is that if you know this if you have lower indices, we are antisymmetrize the derivative down with the lower indices. And what happens, again, it's kind of like magic. This actually is the same thing with the derivative up when you're contracting the derivatives.
Mm-hmm.
So again, the coincidence, I think not, but I don't know what it means. And then the other thing that is interesting is that when you do the inverse of the EM field, you don't get the up version of the derivative, but you get something else. Like there is a difference, and that difference is exactly the four potential contracted with the last index of the G alpha beta gamma.
Mm-hmm.
And then there is another cute thing is that the antisymmetrized covariant derivative is the same as the antisymmetrized standard derivative. It is not true for the upper version of the covariant derivative. And what you find is that the difference between the sort of antisymmetrized covariant derivative and the antisymmetrized standard derivative is exactly that G alpha beta gamma.
So it looks like a connection in some sense.
Yes, like it definitely has some geometric information. I do not know what the geometric information that is giving me is, and I've never seen it in any textbook that does, pseudo-Riemannian geometry or relativity. And I'm so surprised because this just came out of simple calculation. It's not like something that I had to work so hard to get. So it's still mysterious to me what it is and what it represents. I had somebody that wrote me a note that I started looking at, but that also like didn't give me like a precise understanding. So. And question from the chat, should we think of G as the matrix analog of the EM field tensor? I'd like to think so, but I don't know what exactly it means. Like as I said, I kind of would like to think it as the inertial forces, but I have no reason to say that that's the case. Like it would be nice if there was some derivation that says, oh yeah, look, you're calculating, I don't know, the energy of the inertial forces, and to do that, you're using that in the way that you would expect a field tensor to do. I really don't know. I'm very open about saying the things that I don't know, so that maybe somebody can help me figure it out. You can finish the paragraph, Tobias.
Okay, the expression G alpha beta gamma is linked to a sort of covariant exterior derivative for vectors. Unfortunately, we do not truly understand its geometrical significance.
And then there is just another bunch of math. I'll probably just talk over it. So now to find the equations for motion, we calculate the Poisson brackets, right? Because that's what we do. So the Poisson bracket between x alpha and x beta is the same as q alpha and q beta, so it's just 0. If you do the Poisson bracket between position and the velocity, again, it's just a matter of putting things in and doing the calculation. And what you find is just, it's 1 over m, the inverse of the metric tensor. So again, the metric tensor reappears whenever you're doing simple things in Hamiltonian mechanics on the extended phase space. And then the other thing that you need is the Poisson bracket between velocity and velocity. And again, this is just computation. There is nothing strange about this. And when you're all done with all of this, you get essentially the upper version of G contracted with the for velocity, and the upper version of the M field. So if you are, so I know for a fact that this G is 0 if you are in Cartesian coordinate in a flat space, which makes sense because the Christoffel symbols would be 0 at that point, and you're taking differences of Christoffel in 0, so 0, 0, it just goes away. And so you would have that the Poisson bracket between the for velocity and for velocity is simply the M field. So again, it's nice to see that all these things that one defines in relativity, they just come out like just by doing the standard calculation that you do in Hamiltonian mechanics. Okay, so again, this is just a bunch of calculation. So I'll just go and talk over this as well. So we find the evolution of the kinematic variables by calculating the Poisson bracket with the Hamiltonian constraint. So these are just Hamilton's equation. you go and calculate the Poisson bracket. And since we already calculated the Poisson bracket between the position and velocity, and the momentum constraint is going to be written in terms of position and velocity, this calculation becomes very easy, and you get what you would expect, that the change of the position with respect to the affine parameter is the form velocity, because that's good. And then when you go and do the change of the form velocity with respect to the affine parameter, you have this big calculation that leads you to this result. So you have dSu alpha is equal to plus q over m, let's say the m field, f contracted with the form velocity, which you would expect. This is the Lorentz force. And then you have essentially twice of the velocity contracted with the Christopher symbol. And if you go and look and use the sort of the covariant derivative definition, this part is just this part. So you get exactly the equations of motion on curved space-time that you would use in differential geometry and in general relativity. So this is the cool thing. Everything works. We didn't know anything about Riemannian geometry. None of these things were defined. We just the G alpha beta, if you remember, comes out just by saying I have a linear relationship between conjugate momentum and form velocity. That's it. That's the only assumption that we had. And all these things comes out, and it just works in the way that you would expect it to work.
What were all of our assumptions to get here? So basically, we extended the phase space, right? And then we assumed kinematic equivalence.
Yeah.
And is that it? Or
Yeah.
correct?
Yeah. And of course, deterministic and reversible evolution, right? So we have deterministic and reversible evolution, independence of the degree of freedom, and full kinematic equivalence. The only difference from this and what we had before is that we treated the time correctly, right? We didn't, we separated the role of the affine parameter and time, right? We separate those things so that time now becomes a variable, so a variable such that we can make coordinate transformation that mix space and time, which means that the coordinate transformation is also going to mix momentum with energy. And it all comes out.
That's really cool. But yeah.
Yeah. Another comment from Louis, it feels like we are inherently evaluating the metric and thus position as something special, more important than other degree of freedom. So the thing that is more important, we'll see it later when we do the reversing of phase space. The position and the time are essentially the variables that define the units. And if you're assuming kinematic equivalence, you're also saying that those elements do not only define the units, but they're enough to recover the dynamics. So the assumption of kinematic equivalence does elevating position as something more important, because you're saying, I just need to see the position over time and I can reconstruct momentum. So you kind of lose the symmetry between the position and momentum at that point, because you're saying position is really the thing that is important. Okay, so I'll finish the paragraph here so that then somebody else can start. These are the geodesic equation modified by the electromagnetic force, which are consistent with general relativity. Here you get the geodesics. Artem, you can.
We have found that the addition of assumption of kinematic equivalence in the generalized case gives us relativistic mechanics and only relativistic mechanics. There was no choice at any point, therefore, in the sense, relativistic mechanics is the only option, I guess it should be,
Yes.
that works. So inside 1.169, relativistic mechanics is a consequence of determinism and reversibility, of independence of degrees of freedom, and of kinematic equivalence.
Let's see how the Minkowski metric and the speed of light emerge from what we have already discussed. The strong kinematic assumption imposes a linear relationship between velocity and momentum, which, in the absence of forces, can be written as p alpha m times metric times velocity. Given that the metric is a symmetric tensor that depends only on spacetime, it can be diagonalized at a point P with a suitable coordinate choice. While the velocity is in terms of an affine parameter s, we can express it in terms of time, since ds x alpha is just doing the chain rule, and then I'm getting lambda dtx alpha. Since we can set x not equals t, the above equation becomes, so here you're just integrating and imagine, and you get the minus energy, dt is just 1, so this is just minus lambda m g00, and then pi is m gi, and then you get the velocity for the x component. Dimensional analysis on the spatial components tells us that already work in the sense that GII must be pure numbers. I'm not sure I understand this sentence. I'm sorry.
I don't either, so I don't blame you, and I think I wrote it. So dimensional analysis of the spatial component tells us that already work in the sense that GI must be pure numbers on the assumption that S has dimensions of time. I don't understand what I was trying to say here. Okay, let's continue the paragraph and let's see if I can decipher what I was thinking years ago.
For the time component, instead, dimensional analysis tells us that G00 must be the square of a velocity. As we saw before, solution with positive energy are those for which S and lambda are aligned. Therefore, G00 must be a negative quantity. Therefore, we said G00 equals minus c squared, and we recognize c as the speed of light. Note that technically the constant does not play at all a role of speed in this discussion, just as a compression factor from the temporal component of the for velocity to the energy.
Okay, so I think this should just have been a dimensional analysis of the spatial components already works in the sense that GII must be pure numbers under the assumption that has S as the dimensions of time. I think that's what it should be. So I'll make a note. And then the idea is that for the other one, the dimensionality that does not work, then you look at the dimension and you say, okay, that thing must be a velocity.
Okay, we can change units so that G00 is -1 and GII is +1. The only good choice of signature. For spatial components, it is just a matter of rescaling the units. For time, units need to be changed as well by setting P0 to -E/c and x0 to ct. Note that the product of the two remains of the same unit, and the two are still conjugate as space variables. Therefore, we have shown that at every point we can find a set of spacetime coordinates such that G alpha beta is eta alpha beta, where eta alpha beta is the Minkowski metric. If we use proper time as the affine parameter s, then lambda becomes gamma, which is 1 over square root 1 plus beta squared, which is squared.
You recover the standard thing. So Louis asks, what if you drop kinematic equivalence assumption? Would everything still be emergent? No. So if you drop the kinematic equivalence assumption, you just have the fact that you have an Hamiltonian constraint. So you just have Hamiltonian mechanics, and you do not get a metric tensor. You do not get any of that. So the kinematic equivalence Elijah, especially the full kinematic equivalent version, puts a lot of constraint. Like it does a lot of work because it basically goes from I have just Hamiltonian mechanics to I have Hamiltonian mechanics with a specific Hamiltonian, right? I don't have all the possible Hamiltonian. I have just that specific Hamiltonian. And I have scalar forces and potential forces and that. And I have a metric tensor. So the linearity relationship between conjugate momentum and forward velocity basically does an outrageous amount of work. And again, as we said the other time, like those are two linear structures. So the fact that you have to have a linear relationship between those two things makes a lot of sense. Okay.
Given that our assumptions or the failure of Galilean relativity, given that our assumptions led directly to relativistic mechanics, non-relativistic mechanics must fail to satisfy the strong kinematic assumption. We have not identified the exact reason of the failure, though we have identified an interesting issue. Okay, I'll continue. Galilean space-time transformations correspond to, so we leave T the same, yeah, the usual stuff. The canonical transformation induced by that space-time variable change is the following. Okay, so
Yeah, I can go through it. First, like I didn't see that Julius was in the waiting room and he raised your hand. So if you have did you have a question or?
Yeah, so I'm a bit confused because if we are going to Galilean relativity, then it might take some time. And I had some questions from the previous part, especially
Yeah, exactly,
about
yeah.
this, G alpha beta gamma. So
Yes.
so I don't know if we should proceed or we could just discuss it here maybe in more detail and then leave it for the next time. I don't know what others think. Yeah.
So Galilean relativity is actually very short. We're not gonna be able to we are not gonna be able to finish if we want to get the question. So let's get your question first.
Okay, so for this, if we go back to this symplectic form and this big G,
Yeah.
so I was doing some reading and I cannot. So I don't know how to classify these inertial forces, and also when it's expressed in derivatives of metrics, it gets me like more confused than if we had Christoffel symbols, because it is possible to express it just as some difference of Christoffel symbols, which is not a torsion, like you said. But what we could also notice is that if you go maybe to the previous page where you have the basis coordinate and yes. So here when we write these bases in symbols E, it might be a bit how to say obfuscating the situation if instead we wrote it in terms of differentials, dx and du. That's another way to write it. I mean, it's just convention. And
Yeah.
And then, so what we know is that the coordinate itself is not a tensor, but this one form is a tensor. While with velocity is that velocity is a tensor, but differential of velocity is not a tensor. So what happens is that if we use this basis, dx du, and we use it to define symplectic form, it is not covariant. If we want a covariant symplectic form, we should use this big D, big differential, where there's Christoffel involved in it. And then what happens is that if we use this covariant basis, so dx and big D u, then in the symplectic form, this part G alpha beta gamma disappears.
Disappears. Okay.
So it becomes, let's say, if we use covariant basis, then we retrieve this expected symplectic form. And this might also suggest that if we use symplectic form to count to compute the count of states, well, we could say that if there is any basis in which this count should be invariant, probably the covariant basis is the one where this is preserved. So
okay. Okay, I'll have to digest and see what is okay. So yeah, that would make sense. So clearly this I'm trying to think because I in another set of notes I did make an intermediate step where I did not have U upper, but I had the kinetic momentum. So I had M this one. So if I use kinetic momentum, it happens what you discuss. I would have that this goes away, and I just have the Q alpha beta. And then because I would be using the uh, uh, let's see, the covariant components of U, then it's exactly as you say. I would have the omega, the expression of the omega in those coordinates would be covariant because x changing one way and mg alpha beta u changing the other way. So yes, so that I had seen. But that didn't, and I understand that this thing appears because I'm using U upper alpha and not U lower alpha. And again, if you are in Cartesian coordinates, those two things are the same thing. And so in Cartesian coordinates, this goes away. But still, the problem is that what I measure is technically the velocity, it's the U upper. And so I still wanted this omega expressed in terms of the things that I measure. Because if I'm trying to measure the lower, right, I need to know the metric tensor. I need to make this calculation. Because when I go and measure the velocity, I literally mean I literally measure a displacement in space divided by a displacement in time. So I'm measuring the upper version.
Yes, I mean, I understand. Yes, even though we might have these covariance notions, but what we measure does not. Well, it's something else. So we could also interpret that in the following way: that let's say we have this have like this non-covariant description, and we have these inertial forces. Then what this G alpha beta should do is probably it is in some sense similar to what we did in the previous time when we had energy and dt, is that when we are how to say, so there is a physical portion of the count of states, and there is another portion of count of states which might be how to say, it's not
okay.
real.
Again, yes, yeah, okay, yes, yeah. I would tend to agree, and that would be the apparent forcing would be the fact that you have to correct these the counts. Yes.
Yes, and now that I'm thinking, yeah, let's say we have some, fluids, and we start moving in some, how to say, non-inertial way through these fluids, and we would notice like energy gain in these fluids. Well, it almost sounds like Unruh radiation if we add quantization to it, because energy is gained from nothing.
Well, I'm hoping that some of those other things could come. The problem of all those things, and I probably mentioned it later, it's right now this is a particle theory, it's not a field theory. So I do not have equations of motion for the fields. And that's a completely kind of work. That's where we would need to then generalize all of this. I mean, if somebody is interested in trying to help me generalize all of this, but yeah, okay, no. So I agree. So conceptually, I completely agree that this thing should be there precisely because we are using contravariant components for the velocity instead of the covariant components. This means that we need to correct the count of states when we are looking at that. And my hope is that this can all be squared by saying, well, inertial forces are there exactly because the velocity is not really counting states anymore in the way that you would expect. It's doing it differently. So if we were able to close all this circle, we would make like a nice explanation of essentially what the relativity is. And then since there is the equivalence between apparent forces and gravitational forces, we might have an idea for gravity itself, right? At this point, the gravitational force here as on the particle, it's because the different shape of space-time basically tells you, yeah, you have to count, since you're not in a flat space, the count of states has to be, corrected by the fact that you don't have a flat space, right?
Yes, and also when thinking, when we have canonical momentum and we express it in this in terms of velocity and the metric, well, in some sense, we are describing information that was contained in one object in terms of two objects. So information has to be the same, but now it is distributed.
Yes. Yeah. Exactly.
So this has to be okay.
Yeah.
Okay, so then next, so then very similar comment is regarding the Poisson brackets, where you have this additional term. Again, so what can be done is that there is a way to define covariant Poisson brackets, and then it does the same. It gets rid of this term away. And
Interesting.
there is a connection. It is not one-to-one, but I think the way it goes that Poisson brackets that how is it that symplectic form can define a Poisson bracket structure, but Poisson bracket structure may not define a symplectic form. There is like this, let's say, not two-way street, and basically to define this covariant Poisson structure, what you need to do is you take the inverse of symplectic form and you contract with derivative of one function and derivative of the other. Yes. And then this would kill these terms. Examples where there is no symplectic form is, for example, motion of rigid body, or spin, or bodies with spins. There might be not this one, both way street, but otherwise, in this particular case, again, if we use if we upgrade the Poisson structure so it uses this big D, then this G alpha beta gamma would disappear, and again we would be left with FAB.
Yeah, and again, if you had the Poisson bracket between the lower indices, this would also disappear, and you would have the lower F alpha beta. So I assume that thing is gonna do something similar like that.
Yes. Okay. Yeah, so I think, this is what I thought. That's the most, I have to say, the least painful transition from canonical momentum to velocities is if we use this covariant forms, and then from there we can jump into these inertial forces if needed.
Yeah. So, but to me is. I actually want this term because I think it's doing something and I want to understand what it's doing. So I don't want to have a notation that hides it. I want to know exactly what is it doing.
Okay,
so it's fine that at some point I write this right, and this that gets good, but I still want to understand like in terms of count of states, because clearly, if I'm using these variables, I am correcting my count of states. So I want to understand exactly why am I correcting by that much, and whether that can give me intuition, essentially, as I said before, on what the gravitational forces are doing. Because I suspect that this is inertial forces, but it should include also gravitational forces there. So
with gravitational forces, there is one aspect is that we have this Einstein's equivalence principle, which says that locally there's not we are falling freely. So if we want to see the curvature explicitly, then what we need to consider is we need to consider extended bodies or systems of particles. So only then we can start thinking. So otherwise, so here it would not be visible. So and that's what exactly.
But since the symplectic form goes into areas of phase space, you are essentially getting you're not at a point. You're in a neighborhood. You're exploring the neighborhood when you're defining the count of states.
Yes. Well, okay. That is a question, because it is. Yeah, it is not always clear when the differential is at the point, when it's differential is a point size or it's actually extended. But because if it only describes a single body, then we should not see a Riemann curvature tensor. Otherwise,
Right, but
if we saw.
if you remember, I don't know if you were there when we discussed Hamiltonian mechanics, we came to the conclusion that what Hamiltonian mechanics is doing is not moving points, but is moving infinitesimal cells. And so the particle state should be thought as a sort of a very tight probability distribution, and that's what you're moving. And so, of course, it has a small extension in both position and momentum, and therefore it will be able to tell these things.
Well, what I've also seen, like if we really want to stick to, let's say, single body, then the spin of the body would couple directly to Riemann tensor. So if we had two index, I don't know, rotation or spin tensor, then that would couple directly to Riemann tensor. Otherwise, we need extended structure. But here it's well, Riemann tensor is a covariant object. So if we wrote a symplectic form in covariant basis, it should appear, but it does not.
Yeah.
Yes. Yeah. So
okay. So there was another comment. I don't know if we should continue with this section. We already are out of time, so maybe we should stop and start these two pieces. But there was a comment for the chat and a hi from regular shorts. So is the failure of Galilean relativity basically showing that assuming kinematic equilibrium already forces a space-time structure in the pre-general way? Yeah, so basically that was going to be the section that we're going to look at next time. It's basically that if you're making Galilean transformations, you are essentially making a small mistake in the count of states because you're essentially changing something that should be space into time, and as soon as if the difference in time are not that large, you're not going to make a big mistake. But if the difference in times are large because you are at high velocity, then you have to be on the extended phase space to make the correct calculation, because you need to treat time as an actual coordinate, not just a parameter. That's basically where the mistake comes. And so once you basically say, I'm gonna do this correctly, you get those corrections and you get relativity by itself. So if we define states on a coarse graining of an observer and we prejudge the observer's scale, then doesn't quantum locally shows that there must be more structure underneath. So there is no coarse graining. The idea is, again, we are mapping probability distribution to probability distribution in phase space. And at a single point, you have a density that is defined, and that density knows about the sort of the neighborhood, because that density is a probability or a mass density, like some amount of mass inside a small area divided by the number of states. So these are local objects, and therefore they know about these things. You don't need to coarse grain anything. It's again and again, I think we discussed it a long time ago. A physical system is something finite that you divide in smaller and smaller pieces. It's not something that you start at points and then you aggregate to do the finite, right? That doesn't work, right? What we do is we start with finite things and we make the assumption that we can make these finite things smaller and smaller and smaller. And as you say, we never measure the density. We always measure some, we have a volume, we measure some mass in some volume, and we measure the volume of that on that volume, and we do the ratio. So the things that exist are always the finite elements. And the fact that we have points is because we're assuming that these regions can be infinitesimally reduced into smaller and smaller pieces. And this is what we're going to see the next time when we do reversing phase space, we will see that that assumption is what's inside the classical mechanics, that you can always take the state space description and refine it and making smaller and smaller and smaller. What happens in quantum mechanics, which is the paper that we actually have to start responding to the comments from the referees, I'm so behind, is that once you say, if you imagine that you have you measure the counts of states, right, and you keep dividing, at some point you're gonna have regions that have less than one state, and you're gonna have to be forced to say that a single point, which is a single state, has no states because it has measure zero. So that's the part in classical mechanics that fails, because it also fails because assumes that there is something like negative entropy, and this is what basically makes classical statistical mechanics not work with thermodynamics and so on. So again, in classical mechanics, there is no coarse graining. You can just make these areas as small as you want, and then such that you can define these densities. If it can be infinitesimally reduced, does the observer not need to hold infinitely much info? Again, it's the finite information is in the finite region, right? The infinite information would be if you were able to make, to increase the resolution to infinite, which you're never going to do. So the infinitesimal reducibility assumption assumes that the points that nature has infinite information with respect to what we can have. But again, it's just an assumption. It's the fact that you're basically, it's not that you are holding infinite information. You are saying that you always have finite information, but you can always get more information. So you basically say, I have this much, like I know that I'm inside here, and that corresponds to some finite information, but I could always get more. So again, the points should be understood. So the question is that in that case, does it even make sense talk about points? That's again what the previous discussion that we have, that these points have to be understood as a limit process, as volume that becomes smaller and smaller and smaller. So that they do not, that they shouldn't be thought as point themselves. Okay, so everything everybody has dropped out, which is fine. I'm not gonna be able to make the reading group next week because in the US it's Thanksgiving, so I am on travel. And so we'll see each other in other 2 weeks. I have another 10 minutes if people want to ask more questions. Otherwise, we'll call it off.
Yeah, I just wanted to maybe get back to the very beginning of the lecture regarding this Hamiltonian constraint and this potential. So I understand that now we are dealing only with individual particles, so that has to be separated from the study of fields. But let's say when we are studying fields and we have, let's say, a scalar field, from what I understand, scalar potential would not affect the symplectic form, but it would affect dynamics because we're differentiating the Hamiltonian. So in that case, it seems that vector potential is not needed if we have that case. Yeah. So if we have, what I read is that let's say we have something like Higgs potential, which is completely scalar field. It is, and it's just for illustration. In that case, what I read is that scalar potential, so U, would not affect the symplectic form. So it would not appear as vector potential or the curvature derived thereof, but it would affect dynamics because we have differential of Hamiltonian. So in that context, it seems that U can exist as a Bonne-Fide function on its own without pushing it to vector potential. But for particle physics, for individual classical particles, I'm not sure if that's the case. However, this would be like very interesting if every scalar function could be decoupled into vector potentials and just pushed into momentum.
Yeah, exactly. I do not know. That's exactly the question that I don't know. So you're right. If you differentiate, let's see, how do I go from here to does it? Yeah, it doesn't appear, right? Because we made the calculation from here. Yes, yeah, it doesn't appear. You're right. And which is, it's like saying that if I had a standard Hamiltonian, the vector potential will also not appear in there. Yeah, I do not know whether this, because at the end of the day, the Q alpha contracted with the G alpha beta give you a term that it's also like independent of P. So if you expressed all of this thing out, this might be able to put it inside the alpha, and then you make a gauge transformation on the P's. But I do not know if that works.
Yeah, because it's it's very general way of writing it. Then what? So it would be very interesting if that can be done all the time.
Yeah, the other thing that you have as another freedom is you could change the affine parameter. So if you make if you I don't have the equation written now, but if you make a change of h, you can make a change of h such that the dynamics is the same, but you're just changing the affine parameter.
Yeah. So yeah, because when we have the vector potential, well, that would see how it directly affects the space, like symplectic structure, the phase space. Yes, we can see in the symplectic form that there is this shearing effect. But does it mean that all the forces, like all potentials, have to affect that phase space, or there might be something else, like, I don't know, just overall scale that does not affect the shape but affects the sizes? I don't know if that makes sense. Yes, and just another comment. So this vector potential here, well, it does not have to be really just this electromagnetic vector potential. It can be come from anything. It can, in principle, it could also be just a constant, basically a reference momentum.
Yeah. It could also be, right? So right now, for example, I'm talking about this as if this is the metric, but imagine that you have multiple particles. In principle, I've said nothing that the G alpha beta for the different particles is the same. Like there's nothing here that is telling you. Like if I only have one particle, this works fine. If I have two particles, I might have a different metric tensor for the two particles. I might have stuff like that. So we clearly need something else to make things work. Which again, it would be the fact that all the particle, the way that you're measuring position and velocity for the particle is the same, and therefore these things are going to have the same metric tensor and so on, right? But again, it also could be that each particle sees a different potential force, which would mean again, you would have to have classes of particles, and these are interacting with different, in principle, different potentials and so on, right? But the point is that the form is still fixed. So even if you say, okay, don't have just electromagnetic forces, I have foo-bar forces, they will still have to follow this, right? In which basically, since we were talking about field theory before, it kind of tells you why the QCD and QED are so similar, right? Because they all follow this form. It's just that you don't have just a single A for QCD. You have the different bees that do not commute and all that. And again, but this tells you that, okay, but the form is actually fixed. So you get these gauge theories, not because of some, coincidence, but it's because the form is actually highly constrained.
Right. Yeah, with field theories, I don't know. I wanted to try to write down like a dictionary, but it's taking some time. So there is one approach based on a cylinder measure, and as far as you know, it's the most successful one in formulating this functional, like say, functional analytic approach to these kind of questions. So for fields, it's basically there is construction of cylinder measure or cylinder pre-measure, and then what we need to take is something like projective limit, and when it exists, then we have this path integral measure, and a lot of things look similar, but to write it carefully, it takes time because unlike with Riemannian measure, in this functional measure, it does not always converge, and then problems may arise.
Yeah,
But
so that's exactly the part that I need to generalize all of this to field theory, because I need a measure, essentially the Liouville measure on function space. And I suspect, so I've looked at the cylinder measure because that's what they use in stochastic processes. In stochastic processes, they need the probability measure over function spaces, and that's what they use. I suspect that the functions that I suspect that we need to find the correct function space first. That the sort of the space of all continuous functions, I think it's gonna be too big anyway. And there is, because I have similar problems in just quantum mechanics. The space, the Hilbert space, the Hilbert space is too big. And if you look at the Schwartz space, then things become a lot more sane. And there is this sense that you think that even when you think I have this infinite space, you don't. You just have a region that then you don't care what happens afterwards. And so the idea that you have functions and therefore fields that sort of go down at infinity faster than any exponential would make a lot more sense. And in all function spaces that one considers, Hilbert spaces and or even the dual of the Schwartz, the Schwartz still play a big role because they're dense in all these other function spaces, and so everything else is just a limit of these things. And so yeah, so these are the open problems that need to be. Once we find the right function space and the right definition of measure, which I think is going to be something simple like a cylinder measure and stuff like that, I think that a lot of the results that we have can be just generalized. In fact, that you can see the finite dimensional case as a particular case of this more general case, which is actually what I would like.
And I was also thinking if it's even possible to, let's say, don't rush to the limit of infinity, but actually start with this cylinder measures, starting with one mode, then adding second mode, third mode. Maybe that would give more intuition, because sometimes these measures just run away, very abstract, and that's it.
Yeah, so yes, it's a completely open problem. And I think I have to go, but there was a last question from the chat. Does the limit process bottom out at the smallest distinguishable relational multiple things? Just to confirm, when we talk about density here, we're talking about continual limit of discrete relational values, not a fundamental object. As I said, so the thing that exists is the fact that at every volume of phase space, you can ask, what's the probability, right? So you definitely, the measure is the thing that exists. And it would be nice to have everything defined in this kind of measure theoretic sense. Even the values of the fields should be averages taking in so, but anyway, but that's basically the idea. That's the thing that we have. And then the fact that we can express the probability density or the statistical density is the fact that these measures have to be absolutely continuous with respect to the measure that is the state, the state counting measure, the Lewis measure, and therefore, when we evolve, we need to map absolutely continuous measure to absolutely continuous measure, which means the density, the radionegative derivative, must be mapped to another radionegative derivative, and therefore you get all these things. And the problem, I don't have a good way to expressing these things nicely, because you see that I'm jumping between things that you define in differential geometry, things that you define in measure theory, things that you define in information theory, and all these definitions, they're kind of like slightly different every time. And I am trying to work on like creating a framework where I can get one definition to all these things and then derive all of them, all the other pieces. But that's basically the difficulty of talking about these things precisely mathematically, because I'm changing definition every time, right? So I start with a measure, I use the radionegativity to define this density, but then when I'm evolving the density, I'm thinking of a sort of a density distribution on a space. So I'm basically thinking it in terms of just differentiable calculus. But then when I'm talking about the one form, the two form, the symplectic form, I'm using definitions from differential geometry, right? And differentiability there is slightly different than the other thing. If I have a finite dimension, like all these things sort of map to each other in some way and so on. But then, you know, when we want, I'd like to do field theories, and that's why I can't, because like you don't have differential geometry in field theories, and I have no idea what measures of infinite dimensional spaces are and all that. So in that sense, I'm like, in my head, I like the best way that I think about the density is the radionegative derivative, which is this limit of taking things that are smaller and smaller. And does the limited process bottom out at the smallest distinguishable relational update? No, so again, there is no bottoming out, right? You can, again, in the classical assumption, you can take regions of phase space that get smaller and smaller and smaller and smaller. Now, the fact that physically you can't do it doesn't mean that you don't allow it in the math. It's exactly the opposite. It's because you say, I'm going to have a physical cutoff after which I don't care, then you basically say, okay, I'll just let the math pretend that the things exist, right? So I have a real line, right, in the model. I know that I will have you know, a resolution of a measurement such that I can't go below that resolution. But then you pretend, yeah, it's let's pretend that I can still go, and then when I make my calculation, I will truncate at the precision that I want. So this is basically what you do in physics. Like when you have, it's the same thing with you know, with the fact that you pretend that your space is infinite in size. You know that your space is not infinite in size. You have a cutoff, but to make the model nicer, you just you pretend that the space you know, it's infinite, even though at some point you're gonna truncate. So okay. I really need to go now, and thank you everybody for following. Thank you, Julius, and everybody else who already get out. And as I said, next week, no, but in 2 weeks, we'll repeat this.
Okay.
Bye.
Bye-bye. Have a good one, and happy Thanksgiving.
Oh, Jess, Selena, you're also here.
Yeah.
Thank you for staying here for a long time as well.
Yeah, I was just listening, but yeah.
I hope
Yeah.
it was an